Well, incredibly solid. Something you probably first saw pinned up in a classroom. The periodic table of elements.
Yeah, absolutely. It feels complete, right?
Totally. I mean, Dmitri Mendeleev laid it out back in 1869, put the known elements in order, even left gaps for ones he knew had to be out there. It feels like the bedrock of chemistry.
It really is. I mean, one of the most elegant and powerful organizing principles in all of science. But, what our sources reveal is that this familiar chart is surprisingly not a finished story.
Oh.
Yeah, it's actually full of fundamental questions, things scientists are still genuinely puzzled by.
And that's exactly our mission for this deep dive then. We're going to unpack these surprising enigmas hidden within the periodic table based on the material you've shared with us.
Sounds good.
We'll show you that even this cornerstone of science, from the absolute lightest elements to theoretical ones at the very edge, is still a frontier of discovery. Let's unpack this.
Okay, let's start right at that far edge then.
Yeah.
One of the most talked about mysteries in nuclear physics is this concept known as the island of stability.
Right. The super heavy elements, we know that elements beyond uranium, that's Z92, the SHEs, they're incredibly unstable. Their half-lives just get shorter and shorter, right? Often fractions of a second.
That's the general trend, yeah, which makes synthesizing them incredibly difficult, as you can imagine. But nuclear shell theory predicts something interesting.
Which is?
That if you hit just the right combination of protons and neutrons, the nucleus might achieve a special kind of stable configuration. It's like hitting a magic number for both protons and neutrons.
Oh, okay.
So the theory points to atomic numbers around, say, 114, maybe 120 or 126, paired with neutron numbers around 184 as potential locations for this island.
An island where their half-lives could be significantly longer than their neighbors.
Exactly. Longer. That's the idea, forming an island of relative stability in a sea of instability.
Okay, so the theory paints this picture, this stable haven out there. But what does the actual experimental evidence show so far? Have we even gotten close?
Well, that's really the core of the mystery. We have synthesized elements all the way up to 118, Oganesson.
Okay.
But their half-lives are still heartbreakingly short. We're talking milliseconds, maybe seconds at best. We haven't seen anything that lives for minutes, days, let alone, longer.
So element 118 exists, but the island itself, it's still just theory based on what we've actually made and measured.
Precisely, yeah. The exact location, how long the elements there might truly survive, could be seconds or maybe something vastly longer, like minutes, days, even years.
Yeah.
And what their chemical properties would even be, they're all open questions. Synthesizing and studying even these short-lived superheavies pushes our experimental capabilities to the absolute limit. The fundamental challenge is just cramming that many positive charges into one tiny nucleus. The electrostatic repulsion is just immense.
Wow. Yeah, I can see that. It makes you wonder what future experiments might uncover. So, okay, that's one edge of the table. But what about the influence of, fundamental physics on the elements we already know? Especially the heavy ones. The sources mention relativistic effects.
Ah, yes. This is where Einstein's physics really walks onto the stage at the periodic table.
Okay.
For heavy atoms, especially those with these large positive nuclei, the inner shell electrons get pulled in so tightly and orbit so fast, we're talking a significant fraction of the speed of light.
Whoa.
That you have to use relativistic mechanics, not just classical Newtonian physics, to accurately describe their behavior.
Okay, so relativity isn't just for stars and black holes. It's happening inside heavy atoms, too. What are the key ways relativity actually changes how these heavy atoms function, according to the sources?
Well, there are two main effects highlighted. First, something called electron shell contraction. Yeah, because the electrons are moving relativistically, their mass effectively increases. Einstein's EMC right? This causes their s orbitals, and to a lesser extent the p orbitals, to literally contract or shrink. They get pulled closer to the nucleus and bind more tightly.
Okay, so the orbitals themselves get smaller because the electrons are moving so fast. That's wild.
It is. And the second key effect is spin-orbit coupling.
Right.
This is the interaction between an electron's orbital motion, think of it orbiting the nucleus, and its own intrinsic quantum mechanical spin. As the atomic number gets bigger, the electric field from that big nucleus gets stronger, and this interaction becomes much, much more significant. It actually splits and shifts the electron energy levels around.
And these aren't just abstract physics ideas, right? They have real visible impacts on the elements. The sources bring up gold's yellow color as a classic example. How does relativity make gold yellow instead of silvery, like most other metals?
It's a direct consequence of that 6's orbital contraction we just mentioned. In gold, the relativistic effects significantly lower the energy of those 6's electrons.
Okay.
This changes the energy gaps between the different orbitals, particularly between the 5b and the 6's. So when visible light hits gold, it absorbs blue light differently than, say, silver does because of these altered energy transitions. What your eye sees reflected is the remaining light, which comes across as yellow and red.
That's incredible. Just from electrons moving fast and mercury being a liquid at room temperature. That always seems so weird for a metal.
That's another prime example attributed largely to these relativistic effects. The 6's electrons, those two outer ones in Mercury, become unusually contracted and tightly bound. They're almost inert, behaving a bit like a noble gas pair.
So they don't want to participate in bonding.
Exactly. They're less available to participate in the strong metallic bonding that gives most metals their high melting points. Less bonding means it melts at a much lower temperature, staying liquid at room temp.
And this also explains that thing called the inert pair effect in heavier pill block elements like lead and bismuth, where the 6 electrons seem surprisingly reluctant to bond.
Yes, exactly. The relativistic effects amplify that tendency for the outer s electrons to be less chemically available, more inert. But here's where the mystery deepens again.
Okay.
Predicting the precise impact of these really extreme relativistic effects on the superheavy elements we were just talking about, the ones near or on the theoretical island of stability that's incredibly complex.
Right.
Take element 118, oganesson. It's currently placed under xenon and radon, so you'd expect it to be a noble gas. But could relativity make it surprisingly reactive? Maybe even a solid or liquid at room temperature instead of a gas. We just don't know for sure.
And this raises a pretty fundamental question. Could relativity actually mess with the familiar structure of the periodic table itself? Could the periodic law, the patterns we rely on, actually break down or get reordered for elements beyond, say, Z120?
It's a real possibility scientists are grappling with.
Yeah.
The fundamental quantum mechanics, amplified by relativity, could lead to entirely new kinds of behavior we haven't predicted well yet.
Okay, let's shift gears completely then. We've looked at the far end, the superheavies, but what about the very, very start? Even the first two elements, hydrogen and helium, apparently present their own unique puzzles.
They really do. Hydrogen is famously tricky, right?
Yeah, it's usually put in group 1 with the alkali metals because it has that one valence electron, the NS1 configuration. But chemically, it's nothing like sodium or potassium.
Not at all. It can lose an electron, yes, like the alkalis, but it can also gain one to form the hydride ion, H, acting more like a halogen over in group 17. And of course, it loves forming covalent bonds.
So where does it really belong?
Well, its unique nature makes its correct placement a point of discussion for some scientists, even if group 1 is the standard convention we mostly use.
Okay. And helium, what's the issue there?
Helium's configuration is 1s2. Now, structurally, that looks like the outer shell of the alkaline earth metals in group 2, like magnesium or calcium, which end in ns2.
But helium is absolutely, definitely a noble gas. It's incredibly inert, sits firmly over in group 18.
Exactly. So the, let's say, mystery here is that for these very first, tiniest elements, simple electron configuration, while it's a great guide generally, isn't the whole story. Their fundamental small size and the unique stability of that completed first tiny shell make them outliers. They don't perfectly fit the broader periodic trends that develop further down the table.
Interesting. They set the stage, but they're also unique. Okay, let's move down a bit into the middle to lower part of the table. Specifically, the lanthanide and actinide series. The sources highlight the lanthanide and actinide contractions. What's going on there?
Right. This is a really well-established phenomenon, but it has significant consequences and some lingering complexity, especially with the actinides.
Okay, so what is the contraction?
As you move across the lanthanide series, that's elements 57 to 71, or the actinide series 89 to 103, you're adding electrons into inner orbitals, the 4F lanthanides, 5R for actinides.
Right, those blocks usually sit at the bottom.
Yeah, and despite adding more electrons and protons as you go across, the atomic and ionic radii of the elements actually decrease more significantly than you predict just based on adding shells normally. They shrink.
They shrink more than expected. Why?
It comes down to shielding, or rather poor shielding. Those inner electrons are surprisingly bad at shielding the growing positive charge of the nucleus from the outer valence electrons.
Ah, okay.
So as you add more protons to the nucleus, pulling positive charge up, the outer electrons feel a much stronger effective pull inwards. That stronger pull draws the outer electrons closer, causing the whole atom or ion to shrink more than you'd otherwise guess.
Okay, so poor shielding in the F block leads to smaller atoms than expected.
Got it. What are the big consequences of this lanthanide contraction then?
Well, it has a major knock-on effect on the elements in the next row, the third transition series, the ones that come right after the lanthanides, like hafnium, tantalum, tungsten.
Because the elements before them shrunk unexpectedly. Hafnium, for example, ends up having almost the exact same atomic radius and charge-to-size ratio as zirconium, which is directly above it in the second transition series.
Wow, so period 6 elements are the same size as period 5 elements in that block.
Pretty much. And this size and charge similarity means their chemistry is surprisingly similar too. Historically, this made them incredibly difficult to separate from each other.
Ah, I see. That makes sense. And the actinide contraction, you said it was more complex.
Well, broadly similar, but the energy levels of the 5, 6 bens and 7s orbitals in the actinides are all very, very close together. This mixing leads to the actinides displaying a much wider and more complicated range of oxidation states and bonding behavior compared to the lanthanides. They're just trickier chemically.
And thinking speculatively, way down the line, if there were ever a G block of elements, predicting how contractions might play out there is purely theoretical right now, yeah.
Oh, entirely. We're just extrapolating based on current theory. We have no data there.
Right. Okay, now let's look at a different kind of pattern highlighted in the sources, one that doesn't follow the usual vertical groups or horizontal periods. These knights move or diagonal relationships.
Yeah, like a knight on a chessboard, moving 2 over and 1 down, or vice versa.
Between certain pairs in the second and third periods, right, like lithium and magnesium, beryllium and aluminum, and boron and silicon.
Exactly those pairs. Even though they're in different groups and different periods, they show these striking similarities in their chemical properties.
How so?
Things like their charge density, their electronegativity values are often quite similar, and they tend to form similar types of compounds, maybe similar oxides or chlorides, things like that.
Okay, so what's the explanation? Why the similarity across the diagonal?
It's primarily attributed to their ions having a similar polarizing power, which is basically the ratio of their ionic charge to their ionic radius.
Yeah.
Because of size trends, including some effects from contraction, these diagonal pairs end up with similar ratios.
So the mystery isn't that they're similar, because we can sort of explain it with charge density, but maybe the extent or the predictability of it isn't perfect.
Exactly. While the link to polarizing power and charge density is generally understood, the precise extent and the limits of these diagonal relationships aren't always perfectly predictable. It represents a kind of subtle deviation from the dominant pattern of vertical group similarities that we usually focus on.
Okay, interesting subtlety. Let's talk about another area where our simple rules for how electrons behave seem to, well, break down a bit. Anomalous electron configurations.
Yes.
We all learn the Aufbau principle, Hund's rule, for filling orbitals.
Mm-hmm.
But there are a surprising number of exceptions, particularly in the D block and F block elements.
Yeah, this is where the sheer complexity of multi-electron atoms really shows up. The source gives those classic examples everyone learns. Chromium, its electron configuration is actually R3d5-4s1.
Instead of the expected R3d4-4s2?
Right. And copper is R3d10-4s1, not R3d9-4s2. And it's not just them. There are many, many more: niobium, molybdenum, palladium, silver, platinum, gold. And loads throughout the lanthanides and actinides have these unexpected configurations.
So what's the fundamental principle driving these exceptions? Why do electrons sometimes jump out of the normal filling order?
It really boils down to stability. There's a special extra stability associated with having a subshell that is exactly half filled, like D5 or F7, or completely filled, like D10 or F14.
Okay.
This stability comes from quantum mechanical effects, like electron exchange energy. Now, the energy difference between, say, the 4s and 3rd orbitals is often very small in these atoms.
Right.
So if the atom can achieve a more stable half-filled or fully filled D or F subshell by shifting just one electron, perhaps from the s orbital, even if it means the s orbital isn't completely full anymore, it will often do it.
So the gain in overall stability from the D5 or D10 outweighs the minor energy cost of moving the electron.
Precisely. It's like a trade-off for greater overall stability.
It's fascinating. But the mystery isn't entirely solved, even knowing that general principle.
Not entirely, no. While the principle of seeking half-filled or fully filled stability is generally correct and explains most cases, precisely predicting all the exceptions and the really complex quantum mechanical reasons behind why those specific energy levels happen to be so close together in that particular atom,
Mhm.
or why that exact configuration ends up being the lowest in energy that remains challenging.
So our simple filling rules are really just good approximations.
They are very useful approximations, but the true electron configurations emerge from a much more complex interplay of all the electrons interacting with each other and the nucleus.
It really makes you appreciate the limitations of our simplified models, even the really useful ones. Okay, finally, let's tackle the biggest, maybe most mind-bending mystery the source material touches upon. Is there actually an ultimate limit, like a point where you just can't have any more elements?
Yeah, this is a deeply theoretical and, you could say, somewhat philosophical question at the edge of physics.
Where does the idea come from?
Well, early simpler models, like thinking about a basic Bohr atom, suggested a potential limit around atomic number Z137.
Why 137?
The rough idea was that for the innermost electron, the 1's electron, to stay in its orbit around such a huge positive charge, 137 protons, it would theoretically have to be moving faster than the speed of light.
Which, according to special relativity, isn't possible.
Right. Now, that model was too simple. More sophisticated quantum mechanical models, the ones that take into account the fact that the nucleus isn't just a point but has a finite size, push this theoretical limit higher, maybe up to around Z173.
Okay, 173. And what happens there, theoretically?
Well, beyond that point, according to quantum electrodynamics, QED, the binding energy of that innermost 1's electron could actually exceed twice the electron's rest mass energy.
And the sources call this the sparking of the vacuum. That sounds wild.
It is a wild concept. It suggests that the incredibly strong electric field near such a nucleus could become so intense that the vacuum itself could spontaneously produce an electron-positron pair.
Out of nothing.
Essentially out of the vacuum energy field. The nucleus would then capture the newly created electron, filling the spot, and the positron, the electron's antimatter counterpart, would be ejected. This phenomenon could effectively prevent a stable 1's orbital from even forming around such a nucleus.
Wow. But is that the practical limit?
Probably not. It's generally expected that long before we actually reach Z173, the nucleus itself would become so inherently unstable, just due to the sheer number of protons repelling each other and complex nuclear forces, that it would undergo immediate fission or other forms of decay. Extreme nuclear instability is likely the practical endpoint, probably happening well before we hit that theoretical QED limit.
So the mystery is really what happens right at those theoretical extremes, Z173 or so, if anything could even exist there, however fleetingly. Could it fundamentally challenge our understanding of atomic structure or even the nature of the vacuum itself?
Precisely.
Hmm.
And experimentally, as we've already discussed, even getting to Z120 is an immense challenge. Verifying anything happening near Z173 is, well, currently way beyond our capabilities.
Yeah.
It remains purely theoretical for now.
So looking back at this whole deep dive, it's kind of amazing. We've journeyed from the theoretical edge of existence and the limits of the universe,
Yeah.
delved into how fundamental physics like relativity warps the properties of heavy elements we actually can study.
Right, like gold and mercury.
Circled back to the surprising individuality of hydrogen and helium right at the start, explored those subtle effects of shielding and charge density causing contractions and diagonal relationships, and even found mysteries hiding in the exceptions to our basic electron-filling rules.
It really underscores that the periodic table, while it's our essential roadmap for matter, is far from a closed book. It's not fully understood. Its remaining enigmas are active areas of research, really pushing the boundaries of nuclear physics, quantum chemistry, and relativistic quantum mechanics.
And thinking about how something as fundamental as relativity might make the periodic table behave in ways we can't fully predict for future super-heavy elements,
Yeah.
it really makes you wonder about the nature of the patterns we use to understand the universe, doesn't it? Are they constant, or do they evolve at the extremes?
It definitely highlights the edge of our current knowledge and maybe the limits of the patterns themselves.
Absolutely. Well, thank you for joining us on this deep dive into the surprising and sometimes perplexing mysteries of the periodic table.